Welcome back to the series of lectures on high performance scientific computing. Over the last few videos, we have been discussing different tools with which we can sort of analyze the performance of our codes, improve the performance of also serial codes, try to focus where we can do parallelization. And in this today's video, we will now go further in looking at one more advanced such tool. This tool's name is called Valgrind. So what is essentially Valgrind? Valgrind is a suite of debugging and profiling tools. It has many tools built into one, which basically focuses its efforts on memory management. We know that memory is a key part of any computer program. A lot of the time, most of the codes spent are either waiting for data, so they're waiting for memory. This is true for both host side calculation and also device side calculation if you're using GPUs. If you're using distributed memory machines, sometimes you have to wait for data over the network. Valgrind typically tends to work with serial codes, but what it does is that it detects memory leaks, it looks at invalid memory accesses, and does a lot more things. It is open source and it's widely used and has a lot of inherently built capability, which we will be discussing in today's video. So if you look at the Valgrind suite, it basically has these main tools, which is memcheck, which detects memory errors. You have cache grind, which does cache profiling. If you remember from the series of lectures on memory hierarchy, every processor has a different series of caches, starting right from the lowermost registers, L1, L2, L3 cache to the main memory. And we know that if we access higher levels of cache or higher levels of memory too often, then we can get performance hits. We would like to see how the data gets transferred between these different levels of cache, and that is done using cache grind. We had seen one example of call graph notation using gprof. Here we will see another one called call grind. We also have tools for threading errors called hellgrind when we are doing multi-threaded programs, data race detection, and then for heap profiling. So Valgrind overall is a very powerful tool suite which can do a lot of tasks, and we have to look at each of these tools sort of individually to see how they can help us. The first one is memcheck. The idea with memcheck is to find memory bugs. Now whenever we program, we tend to introduce a lot of bugs in our code. Essentially, when we are looking at is what is known as memory leaks or lost pointers. Many times what happens is that a programmer might allocate a memory and then never use it, or also probably never free the memory. The programmer might also do something like assign a pointer and allocate memory from that pointer address, and then without freeing up the memory, use that pointer to point to some other memory address. So if that happens, what essentially is happening is that the memory which the first pointer used to initially point to, it's still allocated for the program, but now is completely lost because there is no variable which is keeping track of the fact where that address is. Now this is a serious problem, because if programs like this exist, then the memory footprint of this program can keep on increasing substantially. And if you have a buggy code with a leaky memory, it's quite possible that the code will now start occupying the entire possible memory, greatly slowing down the entire program, but not only just slowing down the program, start affecting the entire machine. And especially if you're in a multi-user machine where there are other users as well, this can cause performance degradation not only for you, but also for the other users who are running their programs on this machine. So this is a big challenge, and you have to always ensure that you do not have leaks in your memory. Memcheck also identifies invalid reads and invalid writes, so places where you're supposed to be writing and where suppose you're not supposed to be reading. It tries to identify that. If there is use of some uninitialized memory, let's say that you have reserved some memory, but you have not initialized it to any value, and then you're going to use it in some calculation. This is a pretty dangerous phenomena, because it's usually programmers assume that if a variable is not initialized to something, the value of it is probably 0, and then they will tend to use it. But that's not correct. It could be any arbitrary value for uninitialized memory, and then you have to be very careful when you have to use this. So if you use certain flags, memcheck will actually go and tell you which variables are not initialized, and you will then get an opportunity to analyze your code and debug the code and initialize those memory locations correctly. It provides very detailed error reports. So how do you go about using memcheck? So to use memcheck, you have to use a command valgrind, use the flag ---- leak check full and whatever the executable is. And then if you want to show all sorts of leaks, then you have to add the other flag ---- show leak kinds all, and then do the program. So you then have to interpret what the error messages are, what the leak summaries are. So now let us just look at an example of a leaky memory, a code which has some memory which has not been utilized correctly, and then we will compile it, we will run it, we will see how Valgrind detects this error. So here's the code with the memory leak. Okay, this is a very simple code where what essentially I am doing is that I have a pointer which is now allocating size of int, and I'm just doing an invalid memory access, which is essentially out of bounds. Remember, in C style numbering, the indices start from 0, right? So 0 to 4 is the index for this particular pointer, because you are done a malloc of 5 times the size of int. Now you're allocating this memory, you're also not deallocating this memory. So you're committing two kinds of errors. One is the absolute gross error of accessing something which is out of bounds, and then finally you're not deallocating memory. So first let us just compile this program, because this program semantically looks correct and it will actually compile correctly, right? So there's nothing wrong with this compilation going on over here. And when I try to run this, it'll just run without any issues. But then if I want to see what's really going on, I'll just say valgrind ---- leak check. Leak check is equal to full. And then me.out. So when you run this, so you can now see that it is actually giving two different kinds of error. One, it is saying that it is doing an invalid write of size 4. 4 bytes is the size of the integer in this program, and it's doing an invalid write because you're not supposed to write out of bounds when you're doing pointer -5. Also, we say that we have not deallocated the entire array, pointer array, which is of 5 integers, which is 20 bytes long, and because we have not deallocated it, you see that you have a message which saying that I have lost 20 bytes in one block, which is a loss of record 1. So you have one record which is the pointer, which is pointing to the start of that particular array, and that record is lost because we are not deallocating it, and we lose 20 bytes of this data. So you see now you have this full set of errors over here, where you have an invalid write of size 4, and also you have this leak. See, this kind of error is sort of really important for you to detect, because if you do not detect these errors, especially if you have large programs where you have lots and lots of memory allocation and lots of assignments, this will give you the correct information of what is happening. One thing I must point out is the fact that when you run Valgrind, you are running it in some sort of an emulator, because it's actually trying to emulate how the CPU will do these things instruction by instruction. It is actually emulating this entire thing about the memory transfer back and forth. So typically programs, when you're running within the Valgrind environment, they run extremely slowly. So this program has to be used only in the case of where you're doing debugging and some sort of extreme profiling. In general, you would never run codes within Valgrind. This is to be done only at the development stage, or you're having some serious problems in trying to debug this code. So that's when you would use Valgrind. So let's go back to the presentation. So essentially, we need to see what are the different types of summaries we get. We get definitely lost, we get possibly lost as well. So possibly lost happens to when you have some indirect references. Typically, you have pointer of pointers, and then those pointers are then dereferenced over there, and sometimes those can be possibly lost. So you have error messages, which is an invalid read or an invalid write. In our case, it was an invalid write because we were trying to store memory out of bounds, but sometimes you might be able to you might be reading something which is out of bounds as well. Let's say that if I were to take the value of pointer at 5, which doesn't really exist in that case, so that could be an invalid read. The next set of things that we're going to look at is profiling with cache grind, and then also profiling with call grind. So cache grind essentially analyzes cache usage and performance. Call grind is used to generate call graphs and look at execution profiles. These are essentially tools for performance optimization. These are slightly advanced versions of gprof, which we have already looked at. gprof was a very basic profiler, but it still gave us a lot of useful information to figure out where we need to focus our efforts in either optimization or parallelization of the code. First, we will now see how cache grind is used to analyze cache usage and performance. So for this, we will now begin with a simple matrix multiplication code. So this code is basically two matrices A and B, which are 512 by 512 in size, and we are now initializing another matrix C to be 0. We are filling the matrix A with random numbers. We are filling the matrix B with random numbers. We are doing this only for the purposes of just calculations. They really do not have any useful mathematics at this point of time. So then we have a matrix multiplication code over here, where we loop over the three indices I, j, and k. And then we are computing Cij is Aij k into Bkj. And we know that in C we have a row major order of the matrix storage. So the main function essentially now will initialize the matrices, then multiply the matrices, and it will complete the matrix multiplication. So we need to now figure out what is really happening. So first, let us compile this code. And to ensure that we are compiling it with no optimization, we will just put the flag -0, because the compiler sometimes can get smart and look at memory patterns of access and optimize the code by itself. But here we want to demonstrate what the advantage of cache grind is. So we will see to it that first we do not put any optimization, and then we will write an optimized version of the code. So I'm going to put in two flags, one for debug and one for saying that please do not optimize this code. And now the thing has been created. So if I just were to plainly execute the code, it will just say I've completed the matrix multiplication. So essentially you will get another random matrix C, which is the product of two random matrices A and B. Now let us run this code with Valgrind and its associated tool cache grind. So that's it. Minus tool, and then I'll give it the executable. So now Valgrind will go and start its emulator, and within this emulator it will then go and do all its calculation. So here Valgrind is giving you an information that this particular processor has L3 cache, and that's going to be the last level cache. So once it does the program execution, it then tells you that there are different types of misses. So I is basically instructions and how many instruction misses are there, and that's pretty low because the code is actually very simple. You're not going to have last level misses for the instruction as much, but that's just about 0. So it's doing about in this case wow, quite a large number of instructions. So I would assume that this is about more than 55 billion instructions is what it is actually executing. It is missing only about 1,000 of them. So that's practically nothing in terms of how many instructions it is missing. But when you look at the data references that it is having, right? So you have a lot of data references. You have about 18 billion data references, and you have a significant number. You have almost a billion of data misses. I may be wrong with the number of decimals over here, but you get the idea that data misses is a significant portion of the data references. And the last level data misses is also significant, which is total D1 miss rate comes out to about 7%. So that means that 7% of the data is not found in the last level cache, and you have to sort of go to the higher levels of memory to sort of go and fetch it. Now, why does this happen? So let us go back to the code and just have a look of what is really happening in the code over here. So if you look at this code, what essentially it is doing is that it is doing matrix multiplication by looping over 3 indices I, j, and k. We know that in C we have a row major order. So if you look at this bit of code over here, is essentially this last loop, you will see that the k index is moving the fastest. So while A is sort of accessed in the correct order, B is not, because when k is moving the fastest, it is actually jumping different rows. So B is now being accessed in an inefficient manner, causing these cache misses. So for this particular mathematical problem, there's no direct way of solving this. Like for example, if I switched the indices around, calling it B, J, K, I'll be actually doing wrong mathematics. But there are certain ways of sort of optimizing this sort of calculation where this sort of dependency comes in. And we can do it using something called as block tiling, I think, which we have discussed in another video. Now I will look at how the optimum optimized version of mat1 multiplication looks like. So here now I'm doing tiled calculation. So first I'm computing what the transpose of BT matrix is. So I transpose the B matrix to get better cache locality, and then I go ahead and do this block sort of computation. So I can then look at this computation in a more efficient manner, and this will give me better cache locality. So now let us compile. This is the same problem. We have the same matrix size 512 by 512. It's just that we are transposing B, and then we are then doing some optimization based on that. Let us again compile, but this time the optimized calculation. And now then let us run this tool Valgrind on this. So here we go ahead, and you can clearly see that this is taking a little bit of time because of the emulation. Here, now that we have finished this, here you can see the number of data miss rate is actually very low. So you can now see that I am having only 0.6% of data misses, and hence this is a far more efficient way of coding. We will now look at the Laplace serial code to see how the performance is. What we have done is we will now reduce the number of iterations for this case so that we don't take too long for analyzing. We just want to analyze a few cache misses. So we will just do about 10 iterations. and we will now see how much time it takes for the Laplace serial code. And then we will now run the Valgrind tool on it, see how long it takes for doing this. And we see that the D1 miss rate at this case is about 12%. Remember, we have done only about 10 iterations over here. Now we can go back to the code and see how we can optimize it by changing the order of the iterations. We go to the compute function and we replace it back to the original way of where we were looping over I first and then j. We do the same for the copy function. We then compile the code and execute it now with Valgrind again. And you can see the data miss rate has dropped from about 12.1% to only about 0.8%. And this was simply because we were accessing the memory in a more efficient manner. So this is how cache grind is very useful for us for general programs to see how we can efficiently access memory. Finally, we have the tool callgrind. Callgrind generates call graphs and execution profiles. And this is important again for performance optimization. So what we need to do is when we are running it, we again have the precompiled tool or the precompiled code Laplace serial. And in this case, now what I'm going to do is instead of using the tool cache grind, I'm going to use the call grind function. When I use call grind, it's going to go and run the code and it says that, okay, I have collected the information. It has so many instruction references, about 739 million instruction references. Now we to see how each of these functions are being annotated. So I will use another command called call grind annotate, and you will notice that a new file has been output, which is called call grind out.181. So I'm now going to use call grind annotate and look at the annotation for this. So again, when I do this, you will see that the whole code sort of skips through. I'm going to sort of redirect it into a text file so that I can read it easily. So I will redirect it to a text file called grind.txt. And when I look at it inside, I will now see what the total number of instructions are. You can see that the compute function takes about 70% of the instructions. You remember gprof gave you timing based on how much actual wall clock time it took, whereas here we are getting ratios in terms of the instructions. So the compute function takes about 70% of the instructions, the copy function takes about 25% of the instructions. Main is obviously taking very few because the child functions are taking all the instructions. And you can see that how many instructions are being done at each particular line. You can go line by line and say that, okay, initialize takes so many instructions, set boundary conditions takes so many instructions, each of the index calculations takes so many instructions, copy is taking some instructions, and you can clearly see where the code spends most of its time. And this information is really useful to again figure out where I want to sort of optimize my code. Similarly, you have other tools which are called Valgrind, which detect data races and other threading errors. This is essentially important for when you have OpenMP codes, and it is essential for multi-threaded applications. So if you go back here, I will show you a simple example of where there could be data race errors. So you have a code called race.c which I have created. So where you have a shared variable, and then basically you look at the variable counter. Counter is going to have a race condition because it has unsynchronized access. So I am then now going to compile this, gcc. I have to give the openmp flag, fopenmp race.c, and then when I say valgrind minus tool helgrind a.out, and it will say there are possible data races of read size 4. So every time you go and try to update the counter, you can see that this code is trying different threads. So we have like 4 threads which are running. You have different threads which are creating the data race in this, and then it says, okay, the final counter value gets to 0, but there's a lot of data race over there. So Valgrind is a very useful tool for us to look at this sort of analysis, but you have to have certain considerations in your mind. First of all, Valgrind slows down execution dramatically. There's a huge performance overhead, so it's never useful for doing things in a real-time application. It can produce very large output files and many complex libraries. Let's say that you have a code which is now linking to different libraries, and then that libraries are linking to other libraries. This can cause false positives in Valgrind. So you have to use Valgrind in the early stages of your development where you're looking at trying to optimize a code. Thank you.